Okay, let me start. So welcome to the Sharjah Academy for Astronomy, Space Science and Technology. And we are very, very grateful to have you all with us to celebrate the IAU celebration, Women and Girls in Astronomy or in Science. So we are having a couple of lectures every week for this contest. And we thank Mariam Al-Qasimi for being part of this celebration. So just to give you a little bit of background about Mariam, she is part of the High Energy Astrophysics Laboratory. She has been with us since about 2.5 years, and we welcome her. She is a graduate from the University of Sharjah, BSc in Physics, and also she has an MSc in Mathematics from the American University of Sharjah. She is working with Dr. Antonios Manosakis and also with her colleague, Ms. Nora Al-Amiri. So we are very, very pleased to have her to give us this talk, and hopefully all of you are going to benefit from it. So the title may be a little bit tricky for some of you. Why gravity is not like the other forces? So hopefully Mariam is going to enlighten us. She's going to give us more information about gravity, about the other forces. Why is it so different, and so on. So we welcome her again. For my student, please, as usual, so by the mid of this lecture, so a link will pop up in the chat. So please use that link to report your ID and also your name. This is very, very important. So hopefully, besides for sure having bonus, also again to benefit from this very nice lecture. So please, Mariam, you have the stage. Thank you very much.
Thank you, Dr. Elias. I hope that you can see me and hear me well.
Yes, we do.
Okay. So hello, everyone. Thank you for joining us today. Today, I'll be talking about why gravity is not like the other forces. So I first explain what are the other forces, and then what is gravity, so we can see the difference between them. And finally, we will delve briefly into why quantum gravity, why we need a quantum theory for gravity, and finally, the summary and conclusion. So let's begin. So what are the other forces? The other forces, we have the electromagnetic force, the weak nuclear force, and the strong nuclear force. The electromagnetic force is you can see it like when you're every day, like how the electricity works and how you can listen to the radio. This is the electromagnetic force. The weak nuclear force is the force responsible for the radioactivity. For example, you can find this and harness this in doing getting nuclear power for nuclear power. So we have an alternative power than fossil fuels. So they use the force of the weak nuclear force to harness new energies. Finally, the strong nuclear force, which is the force that binds the nucleus together. This is the force that they're using it to also use it in the nuclear fusion to have a nuclear power. So these are the three forces. And finally, gravity. With these three and gravity, we have the four fundamental forces of the universe. So why gravity is different from these three? All of these three can be explained by what we call quantum mechanics. That means that we can explain each one of these forces by some elementary particles. For example, the elementary particle for the electromagnetic force will be a photon. So we can have that as the basic particle that explains the force. For the strong force, we have what we call gluons. And for the weak force, we have the W and Z bosons. However, for gravity, we do not have such a thing. That's one of the main reasons why gravity is different than the other three forces. We don't have an elementary particle that explains it. So how do we explain gravity? What is our understanding of gravity? If we can't explain it by elementary particles, we can see it in the next step, which is what is gravity. As you may know that the famous Newton's theory of gravity was like he predicted it and imagined using the famous falling apple. This is one view, Newton's view about gravity. Another view is Einstein's view. So Einstein proved Newton wrong, but let's see what Newton was saying about gravity. So Newton's law of gravity is basic. It just says that it's a force between two massive objects with a distance between them. So if we have an object, let's say a sun, and we have another object, and let's say the Earth with mass m and capital M. So the force between them is just the masses of these two times together over the distance between them squared with a gravitational constant. So this is all he says, that gravity is due to the two masses and the distance between them. So this worked really good for over 200 years, explained perfectly and accurately the attraction between any massive objects. But however, they noticed that it fails in one thing. Like, was a big failure was the prediction of the Mercury orbits, where Newton's law should explain that Mercury's orbit should be constant. It doesn't vary this much. However, experiments and observations showed that Mercury follows a weird orbit like this. So Newton's law was not able to explain these differences in the orbit. So that's why physicists thought that they need another theory of gravity. So here comes Einstein. Einstein said that gravity is not actually a force, but it is a curvature of time and space. What does that mean? To understand what time and space, or time-space, we need to first understand Einstein's famous theory of relativity. So we have first the Einstein's special theory of relativity, which explains what is space-time, but without considering gravity. And then general relativity that considers gravity. So to understand general relativity, which is Einstein's theory of gravity, we need to first understand what is special relativity. So special relativity is a theory based on two postulates. The first is the laws of physics are the same in all inertial frame. By an inertial frame, I mean if an object is moving at constant speed or not moving at all. So if we have, for example, a cat driving a car at constant speed, this is an inertial frame. Or if we have a standing cat as well, this is an inertial frame. So we say the first postulate is that the laws of physics are the same in all inertial frames. That means if we have F equals ma in the car, we must have F equals ma with the standing cats. The second postulate is that the speed of light is invariant to all observers. That means, what does that mean? That means if we try to measure the speed of light in the car, it would be 3 times 10 to the 8 meters per second. It's constant. So is here, it will be constant. These are the two postulates that special relativity relies on. So we can see it in another way. We can forget about cats, and let's say we have a person moving in a train and another standing there. So the person in the train would feel that he's not moving. He knows that he's not moving. However, the person outside the train would say that they are moving. So their motion is relative. And and also if we have F equals ma here, F equals me here. Any law of physics that works here should work here. The other postulate, as I said, that the speed of light is constant. It doesn't change in whatever frame you are. So if we have here the speed of light c equals 3 times to the 10⁸ meter per second, here should be the same. This observer should measure the speed of this light to be c as well. He won't measure it as v, the speed of the train plus the speed of the light. It should be the same. So this is special relativity. This is what's based, what Einstein based his theory on. And with that, he noticed some really interesting results. So one of the interesting result of that is that simultaneity is not absolute. What does that mean? That means if I have an event that I see, two events that are happening at the same time, and another person could see that this event are not happening at the same time. So it doesn't have to be the same for every person looking at an event or two events. For example, if we have a person inside a moving train and we have two light bulbs, let's say this is light bulb and this is a light bulb. They are turned on at the same time such that the light reaches the person on the train at the same time. So he noticed that the two lights turning on are a simultaneous event. They are happening at the same exact time with the objects moving. However, if someone were standing outside the moving train and was witnessing these two events, he would witness that one light is turned on before the other. How is that? Because you're seeing the train moving forward. So a person that was standing here will move closer to this light bulb. So the lights from this light bulb will travel less distance, while the light from this light bulb will travel a longer distance for this person to see the light bulb, the light reach him at the same time. So I know it's a bit confusing, but let me say it again. So if we have a person that is moving in a moving train and he sees two light bulbs reaching lights to him at the same time, this is not necessarily the same if a person looking at it from a distance. So for this person to receive the light at the same time, this person says that one light bulb should be turned on before the other, since he is moving closer to one and moving further to the other light bulb. So this means that this must be turned on first, so it will travel further to reach this person, and this will be turned on after. So because this person is traveling towards it, so it will travel a shorter distance. As you see that this light will travel a shorter distance of D2, while this light will travel a longer distance of D1. So that means simultaneity is not absolute. That means an event that happens at the same time for a person is not necessarily the same time for the other person. This was an interesting event and the consequences of special relativity. Another mind-blowing consequence is the time dilation. So what is that time dilation? If any of you guys have heard of the movie Interstellar, that's how time moves differently with different traveling people and stuff. This is a consequences of special relativity. How can we see that? So, for example, if you were in a spaceship and you have a light bulb here, and we turn on the light on, so it will reflect and go back and here. You can notice here a specific distance at a specific time. We can count it. So this person tries to measure the time this light travels. Then, if someone from afar sees this event as well, he will see that this light travels a longer distance, so a longer than this. So since this light travels a longer distance, and since the speed of light should be constant at all frames, that means this will take a longer time to travel, which means the time measured here is not the same as the time measured here. That means this person will age, while this will stay young. This is what happens in Interstellar, where Matthew McConaughey, if you remember, was crying because he missed his little girl growing up, because time passed slower where he was, while it passed faster for his little girl, and she grew up and he missed almost all of her life. So Interstellar, now you can understand it. So this is really interesting. This means that we used to think that time was an absolute thing, it was not changing, it's the same for all. However, Einstein showed that it's actually a variable. It changes with the speed, the velocity that you're moving with. So he, understanding that, he realized that our universe can be explained by what we call space-time. So he related time with space, how moving something in space can move, it can changes the time experience and time elapsed. And we call that space-time, which is really, really an interesting and fascinating idea if you think about it. Like, you think that someone, yet you experience time differently than another person. It's not absolute. It's a really nice idea. It's an interesting idea. So this is special relativity. It's a bit mind-boggling, but it's really fascinating. So to move on to general relativity, we need to, as I said, general relativity puts gravity into special relativity. When we discussed special relativity, we disregarded anything about gravity. So to move on from special relativity to general relativity, Einstein used what we call the equivalence principle. So the equivalence principle says what? For example, let's say that you are in a box on Earth, not moving, and there's another person accelerating in the space. Okay, so the equivalence principle basically says that if you were in a box, or you were in space moving, or you were in a box on Earth, you would not know the difference between them. You would not know if you were in space or on Earth. That means an accelerated motion is exactly the same at rest in a gravitational field. So this person inside doesn't know if he's on Earth or in space. Similarly for this, he would not know if he's in space or Earth. So this is what we call the equivalence principle. So from the equivalence principle, we showed that if we turn on a light here, the light it will move like this. It will be affected by the acceleration, which you could understand that as you move, the light will also try to take that path. However, using equivalence principle, we just said that this is exactly the same as this. That means gravity affects the light. Even if we were not like accelerating, it will affect the light. But that's interesting because we know that light has no mass. And if gravity is a force affects the light, how does it how can it a force be affecting the light since it doesn't have mass? Because we know that Newton says that F equals mg, which means, but we have m0 for mass of the light. That means the force is 0. But however, we do see a curve in the light. So how is that if our force is 0? That Einstein concluded that gravity curves space-time. Remember the graph of space-time? Gravity will curve it in such a way. So if light passes here, it will be in a place of gravity, it will be curved. So that's why it's curved, not because of the force of the gravity, it's because of the curvature of space-time, not because the force that was given by Newton. So this is really interesting. This tells us that we live in a surface that is like a curvature, a trampoline. Imagine that you are on a trampoline. If you put something heavy in it, it will go down. It will be curved. So this is exactly the universe we live in. This is how gravity is defined in general relativity. So general relativity is a geometric theory of gravity. That means we consider gravity as something geometrical, not a force by an equation. They are equations, but not simple as F equals mg. So, for example, if we have space-time and we have light traveling in this direction, this is the light, then with gravity, it will bend the path of this light. You could see the difference between this and this. That means gravity bends light. That means that gravity bends the space-time diagram here. And the more the mass an object has, the more it curves space-time. For example, we have our sun is less massive than the neutron star, and the black hole are much, much massive, so it curves it really much. So this is the universe we live in. This is how light travels, how everything travels in light in the universe, which is really interesting to think about it. So some interesting thing to think about how our how planets' orbits work. So since the sun is much massive than our planet, it will travel through the orbit in such a way. This is, if you could try that even in your home, if you have something heavy at the trampoline and then you throw something around it, it will keep orbiting in such a way because of the curvature of space-time. Another interesting thing about general relativity, it was able to explain the orbit of Mercury. As I said before, Newton failed to explain that. This is how Newton explains the orbit of Mercury. However, general relativity showed that it moves in such a way which is exactly the same as the observations that was collected, which proved the validity of general relativity. So interesting stuff. Finally, we have some general relativity prediction. What did it predict? What resulted in it? And we have so many experiments that proves general relativity. One of the first ones is proving the bending of light. They were able to prove the bending of light by taking some observations of a star. They say they have found out that they can see the star in this position. However, the actual position of the star was actually here. That means that the sun, the gravity of sun was able to bend the light, proving the curve that gravity curves space-time. Another thing, as I said, is the Mercury's orbit. Gravity did show that it fits the observations of Mercury's orbit. Another thing is black holes. Gravity did predict the existence of black holes, and it was detected and it was proven mathematically that the existence of black holes. This is all started with general relativity. Finally, gravitational waves. There was the LIGO experiment, if you have ever heard of it. It won the Nobel Prize. It was able to detect what we call gravitational waves. These gravitational waves is just like that. You could see it here. They were able to monitor the emergence of two black holes. So we had two black holes rotating each other until they merged. And when they did that, they did ripple in space-time, causing what we call gravitational waves. These gravitational waves were detected in the LIGO experiment and were proven, which is really exciting. And also general relativity predicts the non-static nature of the universe. So far, general relativity seems to work pretty much really good. So what's the problem here? We have some failures of general relativity, and that's why we need what we call quantum gravity. So where does general relativity fit? As I said, we could not explain it using elementary particles like the other forces. Like we had photon for electromagnetic forces, and the gluons and the W and Z bosons. All the other forces we were able to explain it using quantum mechanics, using elementary particles. However, we don't have this in in gravity. So that's why we need quantum gravity. So another thing it fails in gravity fails, the general relativity fails on, is the explanation of black holes. The equations that explains general relativity were not able to explain black holes. They break. They do not work in black hole at the singularity of the black hole. The singularity of the black hole is the most at the last point in the black hole. We call it the singularity. As I said, heavier objects curve space-time, and makes a shape like that. So the last point at the black hole is called singularity, and Einstein's theory does not work here. So that's why we need another theory of gravity. And it also could not explain the first moments of the universe after the Big Bang. Einstein's theory do not work here as well. And as I said, it's incompatible with quantum mechanics. We cannot find elementary particles explaining gravity. So that's why we need a new theory. We need what we call quantum theory of gravity. We have the most famous two are called string theory, which takes an elementary particle as a string, considers a particle as if it's a string. This theory successfully could combine all the four forces in one theory. And we also have quantum loop theory, which explains the gravitational interactions, explains the gravitational interactions as variables in a loop. So we have these two options for explaining quantum theory of gravity. It's looking for the elementary particle for gravity to be a graviton. So just like the other forces, it assumes an elementary particle for the gravity to be known as the gravitons. This is an ambitious thing that it was never proven, and if this was ever found, or if we ever found a quantum theory of gravity, we would find we know as the theory of everything. Good movie if you want to watch it, it's really nice. So what's the problem here? We don't have any proof of it. We cannot even test it. Sometimes it's hard to test such theories, and so on. To end this, I don't know, you guys follow the newsletter that Dr. Elias sends every Saturday, where he shared a really interesting article about proving even Einstein more right, which is really interesting. So sometimes people, scientists, I mean, trying to prove quantum gravity, they try to prove something that will break in a symmetry that will break in general relativity. However, the result that was shared by Dr. Elias' article was shows that it cannot be broken even at higher energy, this thing, which is basically says that it's bad news for quantum gravity, or for string theory and quantum loop theory. You should guys check out the article. It's really interesting. It's another proof that Einstein's theory are really working really good at higher energy. So this is what we got so far. So to conclude that, I want to summarize what I've just mentioned. We saw that the electromagnetic force, strong and weak forces, are explained by quantum mechanics, are explained by elementary particles, the photons, W and Z bosons, and the gluons. These all are elementary particles that explains these three forces. However, for gravity, we do not have such thing. Then we talked about how Newton's gravity is different from Einstein's gravity, how Newton's gravity worked for 200 years, but Einstein showed that he was wrong. We also showed that special relativity shows very interesting results, that simultaneity is not absolute. That means that an event happening for me at the same time is not necessarily happening for another person at the same time for the same two events. And time dilation is real, and that can be seen in the Interstellar movie. Finally, general relativity is a geometric theory of gravity. It showed that gravity is not really a force. It's how our universe is shaped due to the mass of the objects. And finally, if we find such quantum gravity theory, it would be a theory of everything. And this is really exciting to think about it. And I think that's pretty much sums it up. I will be happy to hear you if you have any discussions, comments, or questions. Thank you.
Thank you very much, Maryam. So now I will open the floor. So please, if you have any questions for Maryam, you can You can speak out loudly, or you can just write in the chat your question, please. Any questions? For the student, you have seen the link, so you have 50 minutes to fill. Okay, so you can read the question, Mariam.
Do the gravitational waves affect us on Earth? If so, how? It does not affect us because it's like, it does affect us like that. We can measure it on Earth. It was measured by the LIGO experiment. The LIGO experiment took like two parallel paths of a mirror, and they said how that, and they shot a laser beam between these two, and they showed how the path differs because the effects of the gravitational waves. So we can measure it on Earth, but we cannot really feel it. If you have anything else, Dr. Yes, to add on to that question?
Well, she may be asking, does it affect us in a bad way? Gravity is very, very, very weak force, so it does not do anything. And as we said, Mariam, it was quite difficult to measure it at the beginning.
Yeah.
Any more questions, please? Especially from the students. It may be a new topic. It was maybe a new topic for them, but it's very, very interesting how gravity can play its role. And as Mariam said, so gravity, yes, it does bend light. And what happened in 1919 in the solar eclipse, so it was a proof that Einstein was right. And yes, gravity does bend light. It all depends upon the mass of that object. Yes.
I think
Any
it was
question? Yes.
Yeah. I think it was
Any more questions, please?
Yeah. It was a bit too much physics, I guess, for all.
Well, you didn't write complicated questions, so but for maybe some of the physics students, for sure they have seen those equations. But for sure they heard about Interstellar, so I believe you explained to them why is it so.
Yeah.
Okay, more questions, please. Okay, so if there are no more questions, so we thank Mariam Al-Qasimi again. Just a reminder, Mariam Al-Qasimi works with us at the High Energy Astrophysics Lab with Dr. Antonios and Ms. Noor Al-Amiri, and she has been a plus for us. And she is a US physics graduate. So we thank her for that. And hopefully, student, you did benefit from this lecture. If it was a little bit hard to follow, so this is very, very simple topic. Hopefully, you get acquainted to it. Some people are asking for the link. The link, if you go to the chat, the link is there. So please, if you go back to the chat, you can see the link. You can go up. Okay. So we send the link at 1:29, so you can read it, SAASST.ee/certificate. It is still working. It will be working until about 1:45. Okay. Okay, so the link appears again for all of you. So please take note of it. Okay, so this coming Wednesday, there is another lecture. It will be given by Ms. Noor Al-Amiri. It will be about the large accelerator, the HSC, and hopefully it won't be very, very technical with Noora, and hopefully you will be able to follow it. This research assistant are physicists in the first place. Sarah, she is asking which time, so it will be this coming Wednesday, yes, Sarah, to be at the same time, 1 p.m. And I will send a poster about it. Okay, so we'll get to know when exactly. This coming Wednesday at 1 p.m. as usual in the Zoom. Okay, so thank you again, Mariam. So thank you for this nice lecture. And we'll have you, inshallah, next time, inshallah. So thank you for all the students who are attended. Thanks for all the faculty members who have attended. So we'll meet you, inshallah, next time. Take care of yourself. Assalamu alaikum.